right, we're back with our Unit 3 list. So today we are going to be focusing on using the graph of the first derivative to determine where a function is concave up and concave down, again based on the first derivative, f prime. We're also going to be determining if a function has an inflection point from the graph of the first derivative or, the second derivative. Blank slide. Okay, so concavity, points of inflection, and the second derivative test for extrema. This we're going to focus on in the next video, the next class, but today we're going to talk about concavity and points of inflection. So by definition, an interval on a graph is said to be concave upward if f prime of x is increasing. So what that means is if I'm looking at the original function f of x, here's my original function f, and I tried to talk about f prime. Well, if I start drawing in tangent lines, this has a really negative slope. Negative slope, less negative, 0, positive, 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 whoa, positive. Which means that if I were to graph f prime, I would have negative numbers through 0, continuing on, positive. So f of x is concave up. I only use that abbreviation when I'm taking quick notes. You should write out concave up. When f prime of x is increasing. Okay, so a graph then is said to be concave downward if, you guessed it, f prime of x is decreasing. So if I draw f of x, this is what concave down looks like, because f prime of x, if I start drawing in tangent lines, these are positive, 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 not so positive, getting to 0, then they switch to negative, 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 negative. So if I were to sketch a graph of f prime, I'd be in positive territory, cross through a 0, down into negative territory, f prime of x would be decreasing. So you might be asking, well, Ms. Schwartz, how do I know where f prime increases? How do I know where f prime decreases? Because so far all we've talked about is where does f increase and where does f decrease. Well, if we think about that, the second derivative is just the derivative of the derivative. Oh no. If f prime of x is increasing, then f prime of x is greater than 0. And if f prime of x is decreasing, that means f prime of x is less than 0. So we can use the second derivative to test for concavity, or we can use the first derivative and seeing if the first derivative is increasing or decreasing. So a helpful picture, all the feels. A graph is concave up if the second derivative is positive. A graph is concave down if the second derivative is negative. I'm going to give you one more chart too on this page. I think there's room at the bottom of your notes. So let's talk about all the ways we can describe f of x. F of x can be increasing. F of x can be decreasing. F of x can be concave up, and f of x can be concave down. Those are the 4 different curvatures, that should be down, that we have on a graph. Well, what that means then is f prime, the next layer, if f of x was increasing, then f prime is positive. If f of x was decreasing, then f prime, the slope, is negative. If f of x was concave up, then f prime, we just talked about, is increasing. If f of x is concave down, then f prime is decreasing. Whoa, so many layers going on. Well, what does that mean about f double prime? This doesn't have any information, right? We can't tell anything from just positive, negative what the next layer would be. But if I think about this, increasing function, the layer below it means positive. So if f prime is increasing, then the layer below it is positive. Likewise, if f prime is decreasing, then f double prime is negative. So this chart is super helpful because then based on if you're given f, f prime, or f double prime, you can find different information about what's being asked. So to test for concavity, we can figure out when f double prime is equal to 0, or where f double prime is undefined. We've seen this before. Previously, we called these critical numbers, where f prime was 0 and f prime was undefined. Here, these are going to determine what we call possible points of inflection. All right, so a possible point of inflection is going to, again, determine intervals. And then again, we're going to do a number line test, except this time we're going to do a second derivative, checking to see if the second derivative was positive or negative, because that then tells us what the first derivative was doing, which then tells us what the original was in terms of concavity. All right, so let's talk about this. If I have a graph like this is my f of x, then all the places where f prime was 0 are going to translate into zeros on my graph of f prime. I have, keep my color straight, come on Schwartz, increasing, so above the x-axis, decreasing, so below the x-axis, and then increasing, so we're back above the x-axis. Well, then if I were to think about f double prime, now I'm going to take the zeros from f prime, oh my goodness, it hurts, and I'm going to look at this part was all decreasing, which means below the x-axis, and what color haven't I used yet? We'll go pink. This part is increasing, which means the derivative should be above the x-axis. All right, well, let's put this together then. This x value happens to be, oh my goodness, right there. What a coincidence. It's not a coincidence, it's how it's supposed to happen. This was all concave down, and this was all concave up, because our first derivative, f prime, was decreasing, which means f double prime is negative. Oh gosh, it hurts, it hurts, it hurts. F prime here was increasing, which means f double prime needs to be positive. All right, we're going to spend a lot of time talking about this. This is a pretty big topic, but let's talk about just an example of how to apply it, okay? This is all the theoretical stuff. This is all the how do you think about it. Let's talk about how to actually do it, okay? So again, that point of inflection is where the concavity changes. So I used orange for concave down and pink for concave up. I guess that'll be my new color coding system. So we find a point of inflection by doing the second derivative equal to 0 or the second derivative undefined. Just like with maximums and minimums from the first derivative, in order to be a point of inflection, we actually have to change signs, okay? So you can't just have a negative and a negative next to each other. You'd have to go negative to positive or positive to negative. So find the points of inflection. Points of inflection is where f double prime changes sign. It's also where f prime would have changed increasing to decreasing or decreasing to increasing. That's how we want to think about points of inflection, okay? Two different ways to view it, through the second derivative or through the first. Well, I have f of x here, so I'm going to go ahead and talk about the second derivative. Well, to get to the second derivative, I have to take the first derivative. Here's 3x squared minus 18x plus 24 I'm going to cruise right through to that second derivative. I'm going to get 6x minus 18. Just checking my math there. So I want to set this second derivative equal to 0 to find a potential point of inflection. I also need to consider where f double prime is undefined. Well, since this is a nice polynomial, this is never going to be undefined. But we do get a critical number, add 18, divide by 6, when x is equal to 3. Sorry, I shouldn't say critical number. It's a possible point of inflection. All right, well this time 3, my possible point of inflection, came from the second derivative. So I call this number line f double prime. And I'm going to do a test just like I did before. Negative infinity to 3 and 3 to infinity are my two intervals. But now I'm using the second derivative because I want to know about the second derivative being positive or negative. Well, a number between negative infinity and 3, I'm going to choose 0. That seems nice and easy. I'm going to sub into the second derivative. That's going to come back negative. F double prime of, I'll choose 4. 6 times 4 is 24 minus 18 gets me a positive number. So from my second derivative, this interval is negative, and this interval is positive, which means that from negative infinity to 3, my graph was concave down. Again, just doing this shorthand for the sake of notes. And from 3 to infinity, my graph was concave up, which means that there's a point of inflection at 3, comma, I need a full coordinate point on my graph of f. Well, what do I do to get my output there? I need to sub in 3 to my original function, right? Anytime we need a y value, we go back to the original function. So I'm going to take 3 to the third power minus 9 times, well, 3 squared is 9, plus 24 times 3 minus 18, and I get an output of 0. Okay, so the coordinate point 3, comma 0 ends up being a point of inflection because f double prime changes from negative to positive. Now, again, I chose to do this one based off of the second derivative. If I did something based off of the first derivative, I could say it would be because f prime changed from decreasing to increasing. We got to be really careful about our word choice. All right, this next one is a long one. This is taking everything we've learned, doing a full analysis, finding all the things to sketch a possible graph for f. So I want you to pause your video and try to find all of this stuff, and then unpause when you're ready to compare. Pause now. Okay, wow, there's a lot of writing. So f prime is going to help me identify increase and decrease of f and where, so those are x values, where the extrema occur. F double prime is going to help me find intervals of concavity and points of inflection. So what I did is I used the first derivative on the left, first derivative on the left, so here's f prime, that one applied to all of this, and I used the second derivative on the right. So you can go through, I set the first derivative equal to 0, consider where it was undefined, same thing with the second derivative. Then look at my conclusions. Yes, it's a lot of writing, but you should be justifying your answers at all times. So you might want to pause the video to read this, see if we compare correctly. And then finally, I want to point out that a point of inflection has to be a coordinate point. Whereas it only asked for where the relative extrema occur. I chose to actually find those values just because it's easier to sketch the graph. Just sub in 1 to the original and sub in 3 to the original. But it also only asked for where. So technically you fit the criteria if you just said x equals 1 and x equals 3. So that's our final graph. Everything checks out. Remember, we don't have absolutes here because we're not on a closed interval. Let us know if you have questions. We'll see you back.